This tutorial is on polarity and polar covalent bonds. I'm only going to talk about covalent bonds and polarity in this one, nothing about polar molecules. This is just the bonds that make up a molecule, whether or not they're polar or not. The difference between a covalent bond and a polar covalent bond is that in a polar covalent bond, there's an unequal sharing of the electrons between the two atoms. One atom has more of the electron density of the bond electrons than the other atom. And that's the difference between the two, and we're going to try to understand how to determine whether or not a bond is polar or not in the following slides. One of the tools that we're going to use to determine whether or not we have a polar covalent, a non-polar covalent, or an ionic bond is a difference between the bond elements' electronegativities. And electronegativity is going to be defined on the next page, but there is a electronegativity number for each element in the periodic table. And basically it boils down to the electronegativity is the ability of an atom to acquire electrons or acquire bonding electrons during a chemical reaction. And it's loosely tied to the ionization energy, where if you have a low ionization energy, so a low ionization energy, you're going to have a low electronegativity value. And if you have a high IE, you're going to have a high electronegativity value. And the boundaries quickly between the two is we're going to assign some, they're not arbitrary per se, but there are going to be some flexibility in these numbers where they fall. We're going to assign 2.0 as being our boundary between polar covalent and ionic bond for the electronegativity difference between two atoms. And our boundary between purely non-polar and a polar covalent bond of being 0.4. If you have values that are less than that, you're going to be basically a pure covalent bond. If you have values in between here and here, it's going to be some degree of polarity in the bond. And then above here, we're going to consider that bond to be preferentially have electron transfer from one atom to the other. This is not always the case. You can have electronegativity values that are higher than 2.0 but still have polar covalent bonding, and I'll show you some examples of why that is. Electronegativity values are values that measure the tendency of an atom to attract bonding pairs of electrons during a chemical reaction. Linus Pauling came up with a scale, and he assigned fluorine as the most electronegative element, and he assigned it a value of 4. And then the other values were down from that, with the lowest values for cesium and francium, and those are 0.6 to 0.7. Electronegativity is not a value that we can measure. It's loosely tied to the ionization energy of an element. So as I mentioned in the slide before, if you have a low ionization energy, your EN is going to be low. So low ionization energy, low electronegativity. High ionization energy, high electronegativity. And you'll find that the same elements that have low ionization energies, the ones that easily give up their electrons during bonding or transfer their electrons during bonding, are going to be the same elements that have the low electronegativity numbers. And vice versa, the ones that have high ionization energies are going to have the high electronegativities. The only difference is that even though that we have the inert gases that have high ionization energies, they don't have any electronegativity, right? So that's why fluorine is the one with have the most electronegative value on a Linus Pauling scale. The inert gases have electronegativities of essentially 0. So there's nothing. So here's the scale of Linus Pauling's electronegativity values. And again, as I mentioned, the ones that have the lowest ionization energy right here are going to have the lowest electronegativity values, and the ones with the highest energies, highest ionization energies, aside from the inert gases, are going to have the highest electronegativity values. And to determine whether or not a bond is going to be polar or not, or ionic or not, what we do is we're going to use our electronegativity values, the differences between the two, to determine whether or not we have the potential for a covalent, polar covalent, or ionic bond. So let's just look at two systems here to give you an example of all three. So let's look at potassium chloride for one. We know that's an ionic bond, but let's look at potassium, and we know that chlorine. And then we're going to look at silicon, and then we're going to look at dioxide, so that's oxygen, and then we're going to look at nitrogen. And so the first one, the electronegativity value is going to be, potassium is going to be 0.8, and then chlorine is going to be 3.0. So by generally what we do is to subtract the larger one from the smaller one from the larger one. And so we get 3.0 for the chlorine, subtracting from 0.8 from the potassium, and we get 2.2. And we know that that is in the range for ionic, and we know that potassium chloride is an ionic bond because A, it's the electronegativity value is 2.2, and B, it's a solid at room temperature, and that B part is important. We'll show you that. There's a few examples where you do have high electronegativity differences, but you still have covalent bonds. And so the next one is silicon oxide, or silicon, we call the silicon dioxide, so SiO2. And so that one was, the silicon is 2.6, but the oxygen is 3.5. So that's going to put the oxygen here as 3.5, and the silicon is 2.6. And so that's the silicon. And so that difference is going to be 0.9, and 0.9 is greater than 0.4, but less than 2, so that's going to be a polar covalent bond. And the last one is nitrogen, and the difference between nitrogen and nitrogen is going to be 0, because the nitrogen is 3 and the other nitrogen is 3, so they end up being 0 because you subtract the one from the other, and therefore 0 is going to be a pure covalent bond. And we already knew that because nitrogen is a diatomic element, and therefore by definition it's going to have a nonpolar bond. All right, so I'm going to show you examples on the next couple of pages where the electronegativity rule only is not going to suffice to give you whether or not you have polar, nonpolar, or polar, nonpolar, or ionic bond. Okay, so let's look at our friend methane here. Methane is a pure hydrocarbon, and I already know by definition that all pure hydrocarbons are going to have be nonpolar. But just so we can do the math with the electronegativity to show you that, I've written in the electronegativity values for carbon and hydrogen, and since we're only looking at the electronegativity value of a bond, which is this here, we're not concerned. There's no other, we don't have to worry about the rest of the molecules. So the difference between the two is 2.5 minus 2.1 is going to be 0.4 delta En, and we said that already, that's going to be a nonpolar bond for our criteria. And indeed, the polarity in methane is, the bonds are nonpolar. Let's look at another molecule real quick, ammonia. Ammonia as bonds between the nitrogen and the hydrogen, and I've done the math already for you, and the electronegativity difference is just going to be 0.9. Electronegativity of the hydrogen is 2.1, the nitrogen is 3, the difference is 0.9, and we know that ammonia has a polar bond, and that polar bond is a fairly strong one. It's 0.9, and we know that from not only from its just from the electronegativity values, but the way it behaves in solutions and things like that. Our last example is water. Look at the water molecule, the Lewis structure for water. It has 2 bonds in there. Both of them are oxygen-hydrogen bonds, and both of them are going to be polar bonds. And we know that because when I did the electronegativity difference between the two, I got 1.4. And we know that water is a very polar substance by the way it behaves, not only in solutions with itself, but with other molecules. And so we do know it's a polar molecule just based on the electronegativity difference. The other thing too we know is that the electronegativity difference of each bond, the hydrogen and oxygen bond, is a polar bond. The molecule itself is polar, but each bond is polar too. And so one of the other things too is I wanted to show you another trick here. I'm going to erase this stuff here real quick. And what we want to know now is, well, when we do have a polar bond, there's some ways to indicate it without doing the calculations. And there's a couple of shorthand tricks. I'm going to show you one on one side and one on the other. So the shorthand trick is one is you're going to write the delta, the mini delta, and you're going to put a plus and then a mini delta on the minus. And that indicates that on the minus side of the bond, there's more electron density than on the plus side of the bond. It doesn't mean that the bond has a plus and minus charge. It just means that if you look at the electron density in the bond, there's more electron density on the minus side of the bond than the plus side of the bond. So let me just draw that real quick here. I'm going to draw hydrogen and then oxygen, and we're going across view ways here to show you this. And in a normal bond, I'm going to use 2 new colors. In a normal bond, the electrons are shared equally, so something like this. But in a bond that has a polarity of the bond, the electrons are not shared equally. The electrons may be shared something like this, right? Where there's more density on this side of the bond here, there's more density over here than there is here. So the net overall effect is relative to a equal bond where all the electrons are equally spaced. This side here is going to be sigma plus, or excuse me, delta plus, and this side is going to be delta minus. It just means that there's more electron density on one side of the bond than the other side. And the other thing that means is that if you're into a system where there's another molecule nearby, and let's just draw another one of these nearby real quick. I'm just going to put one over here. And then that has the same system here, so this is going to be something like this. These molecules are going to now align themselves so that this charge here finds the nearest one of these here to kind of get together and say, okay, we want to I'm attracted to your large electron density. I need some electron density. I can't get it from my guy. I'm going to try and get it from you. So that's how, and they form a little pseudo bond. It's not really a chemical bond. It's called a hydrogen bond. And the last way I'm going to show you how these sometimes people write these differences in the charges is the following. They instead of writing these little deltas, they actually write this little cross with an arrow, and so they put it like this, and then they go this way, and that just shows you that this is the more positive side of the bond, and the electrons are being pulled in this direction. So again, we just do it over here. It would be the same thing over here towards that way. And it shows you that the electrons are being pulled to that side of the bond. So let's wrap this up on the last slide here. We went through the differences between a polar and non-polar covalent bond, and we differentiated that from an ionic bond. And part of the differentiation was the electronegativity difference. And we assigned an arbitrary value of electronegativity difference between a polar and non-polar bond, a polar and a ionic bond of 2. And there are some exceptions to that. Well, there's a little bit of a leeway on that, right? Sometimes we've seen 1.17 to be an ionic bond, and materials that have 2 or even greater than 2 to be polar covalent. And we also accepted that 0.4 was going to be our limit or boundary between pure covalent bond, where the electrons are equally shared, and polar covalent bonds, where there is an unequally sharing of the electrons. And so those are basically on the electronegativity differences. The one thing I want to say about the difference between ionic bond and pure covalent bond, there are some systems where you would think that there are going to be a purely covalent bond, a purely ionic bond, and they are actually a polar covalent bond. And let's look at that. One of those examples, that's BF3. And one of the criteria for an ionic bond is it has to have a crystal structure or be a solid at room temperature. And it has to have a electronegativity value of close or near or at 2.0 or 1.7, 1.8 in that range. And we know that BF3, if you do the electronegativity, that is going to be equal to 2, but it's a gas at room temperature, therefore it can't be an ionic bond because it's not it doesn't make an ionic solid. So there's other limitations, there's other criteria that you need to fit between making a polar covalent and ionic bond, just besides just electronegativity.